let's jump right into this explainer because we are currently on the verge of a technological leap so profound it literally requires us to manipulate the invisible wave calculus of the universe. Today, we're exploring how quantum mechanics is finally moving out of purely theoretical physics and into the tangible, real-world applications that are poised to completely reshape how we compute, how we measure, and really how we understand the world around us.
So, what actually happens when computers start thinking in waves? It's a question that immediately disrupts all of our classical, binary assumptions. We are so incredibly used to a world of ones and zeros, on and off, true and false. But nature just doesn't work that way at its fundamental level. By setting aside our binary bias right here at the start, we're setting the stage for some truly mind-bending science.
To unpack all of this highly complex physics, we'll just follow this quick roadmap today. We've got 1. The quantum revolution. 2. Taming the quantum waves. 3. Sensing the invisible world. 4. Breakthroughs on the horizon. And finally, 5. The next quantum leap.
Starting off with Section 1, the quantum revolution, breaking the binary limits.
Okay, imagine navigating a massively complex maze. A classical computer is essentially stuck using brute force checking. It runs down a path, hits a dead end, backs all the way up, and tries the next one. It evaluates those paths sequentially, one by one. Quantum computing, on the other hand, uses qubits that can exist in a superposition of states. This means it evaluates possibilities in parallel. But the coolest part? It doesn't just guess randomly. It actively steers the system toward the best outcome by manipulating probabilities. And how exactly does it do that steering? Well, it all comes down to quantum interference. This is absolutely the cornerstone of quantum advantage. Because qubits are described by wave functions, they have what we call probability amplitudes. These are complex numbers that act just like waves. Think of ripples on a pond. These waves can combine constructively to amplify the correct solutions, or destructively to totally cancel out the wrong ones. This is that invisible wave calculus beneath the code that transforms a random quantum jumble into an incredibly powerful computational engine.
Which brings us to Section 2, taming the quantum waves, choreographing the invisible.
I absolutely love this quote from computer scientist Scott Aaronson. It brilliantly illustrates that quantum computers don't just magically know the right answer in advance. Instead, they engineer a highly precise interference pattern. By applying specific quantum gates, the system is choreographed so that all the myriad ways to get a wrong answer cancel each other out. Meanwhile, the paths leading to the right answer align and reinforce. So when you finally measure the qubits, the correct answer practically leaps out at you.
Honestly, think of this whole process exactly like conducting an orchestra. You're arranging quantum operations like individual instruments. The goal here is to leverage constructive and destructive interference so perfectly that all the background noise completely cancels out, and only the desired symphony, your correct computational answer, is amplified. It's this beautiful fusion of math and physics, where the algorithms themselves are literally constructed as interference patterns.
And you can actually see this symphony at work in real mathematical algorithms. Take Grover's algorithm, for instance. It uses a diffusion operator to iteratively shrink the probability of wrong answers and boost the right one in an unsorted database, giving us a massive quadratic speedup. Then there's Shor's algorithm, which uses a quantum Fourier transform to construct interference patterns that reveal the periodicities needed for integer factorization, delivering an exponential speedup. They mathematically prune away the wrong paths to achieve processing speeds that classical computers simply cannot touch. All right, let's pivot to Section 3, Sensing the Invisible World, Metrology and Atom Interferometry. We've talked a lot about computing, but let's see how these exact same wave-like properties are used in the physical world.
I know atom interferometry sounds incredibly intimidating, but it really just boils down to 3 elegant steps. First, laser pulses act kind of like beam splitters, putting an individual atom into a superposition of different momentum states, essentially splitting its physical path. Second, these atomic wave packets freefall and accumulate a phase shift based on the inertial forces they experience, like gravity. Third, you hit them with further laser pulses, acting as mirrors to recombine the wave packets. By measuring the final interference pattern, we can determine the exact forces the atom experienced. It's effectively using a laser as a fine-grained quantum ruler to measure the universe.
Now look at this staggering number, 6.7 times 10 to the negative 12th gram. To put that completely wild metric into perspective, that is like sensing the gravitational pull of a single grain of sand from all the way across a room. No joke. This is the record-breaking acceleration sensitivity achieved by a research team at Stanford University.
By allowing the atoms a long freefall time, they reached an unprecedented level of precision in a single experimental cycle, improving on previous limits by more than 2 whole orders of magnitude. But to pull off that kind of sensitivity, researchers had to build a massive 10-meter-tall atomic fountain. Inside that giant vacuum tower, they are manipulating microscopic atoms chilled down to picokelvin temperatures. And just for context, that is significantly colder than the vacuum of deep space. This extreme, mind-numbing cold is absolutely required to maintain the quantum coherence of the atoms, so their delicate wave properties don't degrade before the measurement is complete. So what do we do with these atomic wave paths? Well, they've become ultra-precise tools. They're already being used as gyroscopes to measure minute changes in Earth's rotation, and as gravimeters that can literally detect underground tunnels or hidden water tables by sensing slight gravity gradients. They're even being used for fundamental tests of physics like Einstein's equivalence principle. We are literally turning quantum superposition into the ultimate real-world measurement device.
Moving right along to Section 4, breakthroughs on the horizon, taking this from the lab to the real world. This right here is why this invisible calculus actually matters to you and me. In finance, quantum interference is going to allow algorithms to analyze vast data sets for portfolio optimization infinitely faster than classical models. In defense, those drift-free atomic accelerometers we just talked about, they will allow for perfectly accurate navigation in deep oceans or environments where GPS is completely jammed or denied. And in pharma, quantum computers will be able to perfectly mimic complex molecular systems rather than just crunching numbers, which is going to drastically speed up the discovery of life-saving drugs. And we're not talking about some distant science fiction century here. The roadmap is already laid out by industry leaders like IBM and major quantum sensing consortia. Right now, we're already seeing the miniaturization of field sensors, moving them out of those bulky lab setups. By 2029, the goal is to hit 200 logical, error-corrected qubits capable of executing 100 million quantum gates. And by 2033, the target is 1 billion logic gates, which is the threshold for unlocking true widespread quantum advantage. Of course, getting there isn't going to be a walk in the park. We have to overcome some major roadblocks. We've got to scale down those massive hardware footprints and cooling systems, but the biggest fight for sure is against decoherence. That's the environmental noise that destroys those delicate interference patterns. The good news is, researchers are making massive strides. New error-correcting codes are encoding information way more efficiently, and large momentum transfer techniques in atom optics are actively clearing the path toward highly stable, usable devices. Finally, Section 5, the next quantum leap. The future is wavy. Let's summarize where this is all taking us. The real practical future isn't about chucking our classical computers out the window. Actually, it's all about integration. We're moving toward a hybrid, quantum-centric supercomputing environment. Classical machines will handle the standard processing, but they'll outsource the most maddeningly complex, impossible problems, like huge chemical simulations or logistics tasks, to quantum accelerators. Simultaneously, we are going to see global networks of entangled quantum sensors monitoring the Earth in real time, mapping underground structures and detecting cosmic shifts with absolute wave-like precision. So as we transition from basic binary bits to this incredible symphony of waves, I really want to leave you with a thought. How will a world governed by quantum precision redefine what you believe is possible? From entirely unhackable communications to discovering entirely new, world-changing materials, the invisible calculus of quantum interference is building tomorrow's breakthroughs right now. Thanks so much for joining me on this explainer. Keep your eyes on the quantum horizon, folks, because the wave is already here.